welcome to the deep dive. You gave us the sources, and we're here to pull out the absolute best, most surprising insights.
Yeah, digging through the latest findings.
And today, we are talking about an incredible piece of engineering, the James Webb Space Telescope. I mean, it's performed so well, it's basically guaranteed itself a future spanning decades.
It's phenomenal, truly. But, and this is the big but, right? That certainty in its operation has thrown up a whole load of observations that are, well, making us seriously question our basic models of the universe.
It's this wild paradox. The better the telescope works, the more confusing the universe looks.
Kind of. It's definitely the ultimate good news, bad news story for cosmology right now. Webb's proving how good we are at observing, but it's also, poking holes in what we thought we knew about the very early cosmos.
Okay, so our mission today is pretty clear then. We're going to dive into the tech stuff behind Webb's amazing lifespan, look at these cosmic controversies. It's stirring up, the early galaxies, maybe dark stars.
In those weird radio circles, too.
Oh, yeah, the ORCs. And then we'll bring it closer to home, talk about the hunt for atmospheres on rocky exoplanets, which is turning out to be really, really tough.
Exactly. We'll try to distill what's critical from all this new data. And it's not just the raw observations, it's the new physics, maybe, and definitely the new ways we have to process the data these findings demand.
All right, let's kick off with the operational status, because honestly, this extended lifespan news is just huge for space science. The original goal, the baseline, was what, about 10 years?
10 years, yeah. That was the design target.
Yeah.
But the launch, the Ariane 5 rocket, it was basically perfect. The orbital insertion was so precise.
Meaning less fuel needed for correction.
Exactly. Way less fuel burned than they budgeted for. So the JWST team crunched the numbers and, well, they reckon there's enough propellant left for a science lifetime of over 20 years.
Wow. 20 years. That's more than double. It changes everything for planning long-term science, doesn't it?
Absolutely. It shifts the whole landscape for what questions you can even ask, what long-term projects you can propose. It buys scientists literally decades of top-tier data.
But it's not just about fuel, right? Space is a tough place to live.
Oh, definitely not just fuel. That's crucial. But you've got the harsh environment. Hardware degradation is unavoidable over time. And a big factor is micrometeoroid impacts. They did have that one bigger-than-expected hit back in May, remember?
Yeah, I do. How did they handle that? Is it affecting things?
Well, the amazing thing is the telescope's still performing above its requirements, just shows how robust the design is. But they have adjusted how they plan observations. They now strictly limit the time the telescope points towards what they call the micrometeoroid avoidance zone.
Ah, okay. So managing the risk for the long haul.
Precisely. It's a constant balancing act to maximize the science while protecting the hardware for those 20 plus years.
So with all this extra time, this guaranteed window, how are scientists deciding what to look at? What's the priority?
Well, it's really interesting. Looking at the latest cycle 4 proposals, there's a huge swing towards spectroscopy, like analyzing the light's chemistry.
Not just taking pictures.
Right. It's about 76.5% spectroscopy compared to only 23.5% for pure imaging. They want the chemical fingerprints.
So they're moving past the, wow, look at this phase and into the, okay, what is this made of phase?
Exactly that. And the instruments getting the most hours reflect that. And our spec, which is great for spectroscopy, gets over 40% of the time. Then MIRI, for mid-infrared, gets about 32%. It tells you the focus is squarely on composition, on temperature, on the nitty-gritty physics. People want the data that breaks the old models.
Speaking of data, this next bit is where things get really cool, technically speaking. Trying to link up the old Hubble data with the new Webb data using AI.
Yeah, this is fascinating stuff. It's using cutting-edge AI, things like image-to-image translation. Think of it like teaching the AI. Here's an old Hubble picture of, say, galaxy cluster SMACS 0723 in visible light. Now predict what the super-sharp Webb infrared image of the same thing should look like.
Creating a bridge between the data sets? That sounds incredibly useful, but you mentioned a headache.
A big one. Synchronization. It turns out these AI methods, especially the paired ones like Pix2Pix, they need the images to be lined up perfectly, like pixel perfect.
And they weren't.
They weren't. Even after using the standard astronomical coordinates to align the Hubble and Webb views, the researchers found they were still off, misaligned by about 3 to 5 pixels.
3 to 5 pixels. That sounds minuscule. Why is that such a big deal?
In the world of deep learning, it's huge. That tiny offset, which standard alignment techniques missed, It's seriously messed with the AI's ability to make accurate predictions. It's actually profound finding.
How so?
It tells us that if we want to really leverage AI for understanding the deepest universe, using data from different telescopes,
Sure.
we need completely new ways to sync them up. We need local, super precise alignment methods. Our old ways aren't quite good enough for the AI era.
That's a really key technical insight. Okay, let's zoom out from the pixels to the biggest picture. Webb's delivering these paradoxes, leading to what people are calling the early galaxy crisis.
Yeah.
What's the core issue?
The crisis is stark, yeah. Webb is seeing galaxies way back in the early universe. We're talking high redshift, around Z15.
And just to remind everyone, high redshift means looking really far back in time, right? Seeing the universe when it was very young.
Exactly. And at that redshift, Z15, our standard model of cosmology, LambdaCDM, says the universe should only be about 500 million years old. 500 million years. Tiny.
Okay.
But these galaxies Webb sees, they look mature, they look highly evolved, complex. Some estimates suggest they look more like they're 10 billion years old.
Wait, 10 billion years old when the universe is only 500 million years old? That doesn't compute.
That's the crisis. A galaxy that looks like a teenager when it should basically be an infant. Now, it's important to be careful here. This doesn't necessarily mean cosmology is fundamentally broken.
Right, not throwing out the Big Bang.
No, not yet anyway. But it's a massive challenge to our models of how the first galaxies formed. The simple versions just don't seem to work. The data is forcing us to consider more complex scenarios. Maybe star formation was ridiculously efficient back then. Maybe early black holes were much more active, making galaxies look brighter and bigger than they really were.
Lots of maybes to explore. And that uncertainty opens the door to even wilder ideas like dark stars.
Oh yeah, dark stars. This is a really speculative but intriguing theoretical idea. The hypothesis is that maybe some of the very first stars, the population 3 stars, made of just hydrogen and helium, maybe they weren't powered by nuclear fusion like normal stars.
So what powered them?
Dark matter. The idea is that if dark matter particles could annihilate each other, and if they got concentrated in the cores of these first stars, well, that annihilation could release huge amounts of energy.
Powering a star instead of fusion.
Exactly. And if this works, these theoretical dark stars could get enormous, maybe up to 1 million times the mass of our sun. And they'd be incredibly bright, maybe 1 billion times brighter.
That sounds completely sci-fi. Is there any observational hint for this, given how controversial it is?
Well, it's highly controversial, yes. Many astrophysicists are skeptical they could even form. But Webb has identified 4 potential candidates that have some characteristics consistent with the idea.
Okay, candidates, but is there anything more specific? A smoking gun.
There's one tentative signal in one of the candidates that proponents point to. It's a specific spectral line. Singly ionized helium absorption at a particular wavelength, 1640 angstroms.
And why is that significant?
Because that specific signature is something you might expect from the surface of a huge, extremely hot star made only of hydrogen and helium, like a POP3 star, or potentially a dark star. It's far from proof, needs tons more observation to rule out other explanations like just supermassive normal stars.
Right.
But it's suggestive enough to keep the idea in play.
Wow. A tiny spectral line keeping a wild theory alive. Okay, while that debate simmers for the distant universe, let's talk about something else. Webb is helping investigate these bizarre, enormous things called odd radio circles, or ORCs.
Yes, ORCs. These are just spectacular. Imagine these vast, faint rings, but you can only see them with radio telescopes. They're made of radio-emitting plasma, and they are absolutely colossal.
How colossal.
We're talking like 10 to 20 times the diameter of our entire Milky Way galaxy. Huge cosmic smoke rings, basically. And we only discovered them about 6 years ago.
Incredible. What did we think they were initially, and what's the latest thinking?
Early ideas pointed towards maybe shockwaves from merging supermassive black holes, or maybe colliding galaxies, creating these expanding shells. But newer research, including insights from simulations informed by observations, suggests something else.
Which is?
It seems they might be linked to incredibly powerful outflows from galaxies, known as superwinds. These are like gale force winds of charged particles blown out by intense star formation or active black holes, usually in spiral galaxies that are also radio sources.
So the winds inflate these giant bubbles or rings in the surrounding gas.
Kind of, yeah. They sculpt the hot, thin plasma that exists between galaxies and clusters into these enormous ring-like structures. The scale is just mind-boggling. One of the newly studied ones, RAD J1222622.6 plus 640622, that thing spans almost 3 million light years across.
3 million light years. That's what, 25 times bigger than the Milky Way?
Roughly, yeah. Just staggering that something so immense could be basically invisible except in radio waves.
Mind blown. Okay, let's shift gears from cosmic rings to something much closer, but just as challenging. The search for air, for atmospheres on rocky exoplanets.
Right. This is a huge priority for Webb, finding potentially habitable worlds, or at least the ingredients for life. And Webb has hit some major milestones here. It's delivered the most precise measurements ever of starlight filtering through exoplanet atmospheres that's transmission spectra. And it made the first detection of heat radiating from cooler rocky worlds, planets below about 800 Kelvin.
Those are big technical achievements, but the headline result so far seems to be nothing found.
Well, it's more nuanced, but essentially, yes. Despite that incredible precision, no definitive atmospheres have been detected on the rocky planets. Webb has studied closely so far.
What are the thermal measurements telling us then?
They show really hot day sites on these planets, which is consistent with them being basically bare rock absorbing sunlight, or maybe having extremely thin atmospheres. We're talking surface pressures less than 10 times Earth's atmospheric pressure, maybe much less.
So thick, high-pressure atmospheres, especially ones rich in CO2 like Venus, seem unlikely for these first targets.
Generally, yeah, they're being ruled out for the planets observed this way. The lack of strong CO2 signals, which Webb is great at seeing, suggests these worlds either didn't have many volatile gases to begin with, or perhaps more likely they lost their atmospheres very early on due to stellar radiation or other processes.
So finding an Earth-like atmosphere is going to be even harder than we thought.
It seems so. To spot the subtle signs of something like Earth's nitrogen-rich atmosphere, maybe with traces of CO2, scientists now talk about the 5-scale height challenge.
Okay, what does that mean in plain English?
It basically means we need about 5 times the current measurement precision just to have a hope of detecting the faint dip in starlight caused by CO2 in an atmosphere dominated by nitrogen, like Earth's. It's a huge observational hurdle. We know the signature we're looking for, but current instruments might just barely be able to glimpse it, if at all.
That really puts the challenge into perspective. While Webb tackles that deep space problem, there's actually something interesting happening much closer to home this October, involving an interstellar visitor.
That's right, Comet 3ILS. This is only the third object we've confirmed came from outside our solar system. And what's cool is its path. On October 3rd, it's going to pass just 30 million kilometers from Mars.
That's pretty close to Mars, closer than it gets to Earth.
Much closer. Its closest approach to Earth is way further out, around 270 million kilometers. So Mars gets the front row seat.
And we have hardware at Mars ready to take a look.
We do. Both NASA and European Space Agency orbiters at Mars, like MAVEN, the Mars Reconnaissance Orbiter, ESA's Mars Express, they're all gearing up to observe it. They'll try to check out its shape, see how active it is, what gases it's releasing, maybe get clues about its composition.
A chance to study material from another star system up close-ish.
Exactly. Plus, ESA's JWST spacecraft, currently on its way to Jupiter, is also planning to take a look around November. It's a coordinated effort to learn as much as possible from this rare visitor.
Very cool. Okay, let's wrap up this deep dive. For you listeners who want to do some observing yourselves, what should you be looking out for in the sky this October, specifically October 2025?
Okay, yeah, a couple nice events. Early in the month, October 2nd, the dwarf planet Ceres is at opposition. That's when it's opposite the sun in our sky, so it'll be at its brightest around magnitude 7.6. You'll need binoculars, but you can find it in the constellation Cetus, the whale.
Nice. Binocular target. What else?
Then on October 7th, we have the harvest full moon, and this year it's also the first supermoon of 2025, meaning it'll look a little bigger and brighter than an average full moon.
Always popular. Any comments for comet hunters?
Yes, 2 potentially good ones. First, Comet C2025K1, ATLAS, another ATLAS comet. Busy Folks reaches perihelion, its closest point to the sun, on October 8th. It's predicted to be around magnitude 5.2. That's definitely binocular territory, maybe just visible to the naked eye from a very dark site. Best seen from the northern hemisphere.
Okay, K1, ATLAS, and the second one.
That's C2025R2, Swan. This one makes its closest approach to Earth on October 20th. It might reach magnitude 7, so bright binoculars again, but there's an outside chance it could flare up and become naked eye visible under really dark skies. This one favors observers in the southern hemisphere.
Good spread then. Anything else notable?
One more nice grouping to look for. On October 23rd, in the pre-dawn sky, you'll see a close conjunction of the crescent moon, Mercury, and Mars. They'll be huddled pretty tightly together. Should be a lovely sight.
Excellent. Ceres, a supermoon, 2 comets, and a planetary meetup. Plenty to look for.
Absolutely. So we've kind of swung from the incredible certainty of Webb's decades-long future to the startling uncertainties it's uncovering about the dawn of the universe, dark matter possibilities, and even how common atmospheres are on planets like ours.
It's a thrilling time in astronomy.
It really is, and it leaves you with this final thought, doesn't it? We're pouring immense effort, ingenuity, technology, decades of telescope time, sophisticated AI models, incredibly precise instruments into answering these fundamental questions about the cosmos. But what happens when the very models we've built our understanding on, the ones we trust for how galaxies form or what planetary atmospheres should be like, what happens when those models are the things that need to be torn down and rebuilt because of the data from our best ever telescope? What assumptions, maybe rooted in the simpler pre-Webb view, are we still clinging to that this new era of precision is about to expose? Now that's the real deep dive for you to think about.